The universe is a vast and mysterious place filled with countless wonders that stretch beyond our imagination. From the smallest particles to the largest galaxies, every element of the cosmos plays a part in a grand cosmic symphony. It's full of wonders that we are only beginning to understand. The beauty of the aurora borealis, the majesty of mountain ranges, and the mysteries of the deep ocean all contribute to the awe-inspiring nature of our universe. One of these wonders is sound. Sound is an integral part of our daily lives, yet it remains one of the most fascinating and complex phenomena in nature. It surrounds us, influences us, and connects us in ways we often take for granted. Sound is more than just something we hear, it's a fundamental force of nature. It shapes our experiences and emotions, from the soothing sound of a flowing river to the calming rhythm of gentle waves on a beach. Think about the last time you listened to music. Music has the power to evoke deep emotions, transport us to different times and places, and bring people together. It's a universal language that transcends cultural and linguistic barriers. Or heard a bird singing. The simple, melodious chirping of birds can bring a sense of peace and joy, reminding us of the beauty and harmony of nature. These sounds, as diverse as they seem, all share a common origin. They are vibrations traveling as waves. Whether it's the ripple of a pebble in a pond, or the rustling of leaves in the wind, these vibrations create the sounds we hear. These waves carry energy, and when they reach our ears, they are transformed into electrical signals our brains interpret as sound. This process allows us to experience the rich tapestry of sounds that make up our world. Understanding sound waves unlocks a deeper appreciation for the universe. By studying how sound travels and interacts with different environments, we gain insights into the natural world and the forces that shape it. From the whisper of the wind to the roar of a rocket launch, sound paints a vibrant tapestry of our world. Each sound tells a story, capturing moments in time and space that define our experiences. Sound allows us to communicate, experience music, and perceive the world around us. It is a vital part of human connection, enabling us to share ideas, express emotions, and build relationships. But how exactly do these invisible waves create the symphony of our lives? The science of sound is a fascinating field that explores the mechanics of how sound waves are produced, transmitted, and perceived. Let's delve into the fascinating science of sound. By understanding the principles of acoustics, we can unlock the secrets of how sound shapes our world and enhances our experiences. Imagine tossing a pebble into a still pond. What happens? Ripples, right? These ripples are waves, disturbances spreading outward from where the pebble hit the water. Sound works in a similar way. When something vibrates, like a guitar string or your vocal cords, it creates disturbances in the surrounding air molecules. These disturbances propagate outwards, forming sound waves. But these waves aren't like those on the pond's surface. They're pressure waves, meaning they travel by squeezing and stretching the air molecules as they move. These compressions and rarefactions, as scientists call them, are the building blocks of sound. They allow sound waves to carry energy through the air, much like ripples carry energy across the water. Now, not all waves are created equal. Waves are fascinating phenomena that occur in various forms and mediums. They can be seen in the gentle ripples on a pond or the powerful crashing of ocean waves on a beach. But did you know that waves can be categorized into different types based on how they propagate? We have two main types, longitudinal and transverse waves. These classifications help us understand the behavior and characteristics of waves in different environments. In an outdoor classroom, a teacher might use simple demonstrations to explain these concepts, while a scientist could delve into the mathematical principles on a chalkboard. Sound waves are longitudinal, meaning the direction of the vibration is parallel to the direction the wave travels. Imagine standing in a field of tall grass, feeling the wind blow through it. The grass moves back and forth in the same direction as the wind, similar to how particles in a longitudinal wave move. Think of a slinky being pushed and pulled along its length. That's a longitudinal wave. The coils of the slinky compress and expand in the same direction the wave travels. This is a simple yet effective way to visualize how sound waves move through air or other mediums. Transverse waves are different. Here the vibrations are perpendicular to the direction of wave travel. Picture a flag flapping in the wind or a tree branch swaying. The motion is up and down or side to side while the wave itself moves forward. This perpendicular movement is a hallmark of transverse waves. Imagine shaking a rope up and down. The wave travels down the rope, but the vibrations are up and down. This is a classic example of a transverse wave. The energy moves along the rope, but the individual particles of the rope move perpendicular to the direction of the wave. Light, for example, travels as a transverse wave. When sunlight streams through tree branches or reflects off water, it demonstrates the transverse nature of light waves. These waves move perpendicular to the direction of their travel, creating the beautiful patterns and reflections we see. Understanding this difference is important because it affects how sound behaves. When you listen to music with headphones or hear birds chirping, you're experiencing longitudinal waves. The way these waves interact with the environment and our ears is crucial to how we perceive sound. The longitudinal nature of sound waves explains why they need a medium, like air or water, to travel. In a pond, waves move through water and bubbles rise through the liquid. Similarly, sound waves require a medium to propagate as they rely on the compression and rarefaction of molecules. They can't travel through the vacuum of space because there are no molecules to compress and rarefy. In the vast emptiness of space where there are no air molecules, sound waves cannot travel. This is why space is eerily silent, despite the presence of stars and other celestial bodies. Section 4, the sound of science: frequency, wavelength, and amplitude. Now, let's talk about the language of sound waves: frequency, wavelength, and amplitude. These three fundamental properties are the building blocks of how we understand and experience sound in our everyday lives. Whether you're listening to your favorite song, hearing the chirping of birds, or even just having a conversation, these elements are at play. These three properties determine everything about how we perceive sound. They shape the way we hear and interpret the world around us, influencing everything from the music we enjoy to the sounds of nature that soothe us. Frequency is how many sound waves pass a point in 1 second. Imagine standing by a river and watching the ripples pass by. The number of ripples that pass a fixed point in 1 second is akin to the frequency of a sound wave. It's measured in hertz, or hertzes. 1 hertz equals 1 wave cycle per second. This unit of measurement helps us quantify the pitch of a sound, which is crucial in fields ranging from music to acoustics. A higher frequency means more waves are passing per second, and that translates to a higher pitch. For instance, the chirping of birds or the high notes of a flute are examples of high-frequency sounds. Think of the high-pitched squeal of a whistle compared to the low rumble of thunder. That's a difference in frequency. The whistle has a high frequency, while the thunder has a low frequency, creating a deep, resonant sound. Wavelength is the distance between two corresponding points on a sound wave. Picture the distance between the peaks of waves on a beach. This is similar to the wavelength of a sound wave. Higher frequency means shorter wavelengths, and lower frequency means longer wavelengths. This relationship is fundamental in understanding how different sounds are produced and perceived. Amplitude, on the other hand, determines the intensity or loudness of a sound. It's the height of the sound wave, and it tells us how powerful the sound is. The larger the amplitude, the more energy the sound wave carries, and the louder it sounds. Think of the crashing waves on a rocky shore or the booming sound of a drum. These are examples of high-amplitude sounds. We measure loudness in decibels or dB. This unit helps us understand and control the volume of sounds in various environments, from quiet libraries to bustling city streets. So, the next time you hear a sound, remember that you're experiencing these three properties in action. Whether it's the frequency that gives the sound its pitch, the wavelength that defines its tone, or the amplitude that determines its loudness, these elements are constantly at work, shaping our auditory world. Section 5. Can you hear me now? Sound's journey through different stuff. We often think of sound traveling through air, but it can travel through other mediums too, like water and solids. In fact, sound travels faster in denser mediums. Think of how much faster sound travels through a solid wall compared to air. That's because the molecules in solids are packed more tightly, allowing the sound vibrations to pass through more quickly. This difference in speed is why whales can communicate over vast distances underwater. Sound travels faster and farther in water than in air. But in the vacuum of space, silence reigns supreme. There's no air for sound waves to compress and travel through. Understanding how sound travels through different mediums is crucial in various fields, from designing concert halls to developing sonar technology for underwater exploration.